What if reality isn't broken, but buffering? What if the strange rules of the quantum world aren't random at all, but symptoms of something deeper, something artificial? At the smallest scales of existence, particles appear and disappear without warning. Time behaves inconsistently, distance loses meaning, observation itself changes outcomes. These aren't just scientific curiosities, they are cracks in the surface of what we call reality. For decades, physicists have tried to explain these anomalies using equations, probabilities, and abstract models. But what if we've been asking the wrong question? What if the quantum realm isn't revealing how reality works, but how it fails? Tonight, we're stepping beyond particles and equations. We're asking a question that blurs the line between physics, philosophy, and something far more unsettling. Is reality glitching because it's being run? And if so, who or what is on the other side of the code? In this video, you will discover why quantum mechanics behaves so differently from the world we experience, and why those differences may hint at an underlying structure we cannot see. You'll explore how concepts like superposition, entanglement, and wave function collapse resemble computational shortcuts rather than natural laws. We'll examine whether the limits of reality, minimum lengths, maximum speeds, and discrete units of space-time, look suspiciously like system constraints. You'll learn why some scientists and philosophers believe the universe may function like a rendered environment, revealing detail only when observed. And finally, we'll confront the most unsettling possibility of all, that the strange echoes of the quantum realm are not errors in our understanding, but messages from the machinery beneath existence itself. Welcome to Where the Light Ends, a place where space grows silent, light fades, and the universe begins to reveal its darkest secrets. Part 1, the quantum realm, where reality breaks its own rules. At the scale we live in, reality feels stable. Objects have positions. Causes come before effects. Time moves forward. If you drop a glass, it falls. If you turn away, the room doesn't change behind your back. This consistency is so deeply ingrained in human experience that we rarely question it. We assume the universe must work the same way everywhere, at every scale. But the moment we zoom in, far beyond atoms, beyond nuclei, into the quantum realm, that assumption collapses completely. Here, particles do not behave like objects. They behave like probabilities. An electron does not exist in one place until it is measured. Instead, it exists as a cloud of potential locations, mathematically described by a wave function. This is not a limitation of our instruments. It is not a gap in knowledge. According to quantum mechanics, the particle literally has no definite position before observation. This idea alone should already feel disturbing. Reality does not merely hide information from us, it withholds it. Even more unsettling is the concept of superposition. A quantum system can exist in multiple states at the same time. A particle can be spinning up and down simultaneously. A photon can travel through two paths at once. These are not metaphors. They are experimentally verified behaviors, confirmed again and again in laboratories across the world. Yet the moment observation occurs, the system collapses into a single outcome. The wave function disappears. One reality is selected. All others vanish instantly. This raises a question that physics still cannot fully answer. Why does observation matter at all? In classical physics, measurement is passive. You look at something, and it remains what it was. In the quantum world, measurement is invasive. It does not reveal reality. It forces reality to choose. Some interpretations claim this happens because measuring devices interact physically with particles. Others suggest consciousness plays a role, though this remains controversial. But regardless of interpretation, the outcome is the same. Reality behaves differently when watched. That alone feels uncomfortably familiar. In computer simulations, environments often exist in a low-detail state until the player looks at them. Textures are rendered only when needed. Calculations are minimized to save processing power. Nothing is fully defined unless it must be. The quantum world behaves in a disturbingly similar way. Then there is quantum entanglement, what Albert Einstein famously called spooky action at a distance. When two particles become entangled, they share a single quantum state, no matter how far apart they are separated. Measure one, and the other instantly reflects that outcome, even if they are light years apart. This does not transmit information in the classical sense, but it does violate our intuitive understanding of space and locality. Distance at the quantum level appears irrelevant. It is as if the universe is less like a vast physical container and more like a connected data structure. Quantum field theory deepens this strangeness even further. According to our best models, empty space is not empty at all. It seethes with activity. Virtual particles constantly pop into existence and annihilate each other, borrowing energy from the vacuum in ways that are allowed only for impossibly brief moments. Reality, at its foundation, is not solid. It is restless, flickering, computational. And this is where the first echoes appear. Because none of this resembles how a naturally intuitive universe should behave. But it closely resembles how a system optimized for efficiency might behave. A system that avoids unnecessary calculations. A system that defines states only when queried. A system where information, not matter, is fundamental. The quantum realm does not feel like the base layer of reality. It feels like the interface, and interfaces exist for a reason. If the quantum realm truly is the foundation of reality, then it raises an unsettling question. Why does it feel so incomplete? Why does it refuse to give us solid answers until we force it to? One of the strangest discoveries in modern physics is that space and time themselves may not be continuous. At extremely small scales, reality appears pixelated. There is a minimum length, the Planck length, beyond which space cannot be meaningfully divided. There is a minimum unit of time, the Planck time, beneath which the concept of duration loses coherence. This is not how a naturally smooth universe should behave, but it is exactly how digital systems behave. In any simulation, resolution is finite. No matter how powerful the system, there is always a smallest unit of space and time it can represent. Below that threshold, detail simply does not exist. Our universe seems to follow the same rule. Then there is the speed of light, the ultimate cosmic speed limit. Nothing with mass can exceed it. Information itself appears bound by this limit. But why should reality have a maximum speed at all? In classical intuition, speed is relative. There is no obvious reason for an absolute cap, unless the universe is constrained by bandwidth. In computational systems, there are always limits on how fast data can propagate. Clock speeds, processing cycles, refresh rates, these are not philosophical choices. They are engineering constraints. The universe behaves as if it too is governed by such constraints. Even energy comes in discrete packets. Quantum mechanics tells us that energy levels are quantized. They jump between allowed states rather than flowing smoothly. This is not a minor detail. It is a fundamental rule. Reality updates in steps. Stepwise change is not how classical reality should operate, but it is how digital systems update their states. Some physicists have gone even further, suggesting that space-time itself may emerge from information. In these models, geometry is not primary. It is derived. The universe is not made of things. It is made of relationships between bits of data. This reframes everything. Matter becomes secondary. Space becomes a visualization. Time becomes a sequence of state updates. At that point, the line between physics and computation begins to blur. And then we encounter one of the most troubling features of the quantum world: randomness. Quantum events do not appear merely unpredictable. They appear fundamentally random. Even with perfect knowledge of a system, we can only calculate probabilities, never certainties. This randomness is built into the equations themselves. But true randomness is rare in nature. It is difficult to generate, difficult to verify, and often indistinguishable from complexity. In simulations, however, randomness is common, but it is never truly random. It is pseudo-random, generated by algorithms designed to approximate unpredictability. If our universe is computational, then quantum randomness may not be chaos. It may be noise. Or worse, it may be intentional variation designed to prevent predictability at higher levels. At this stage, skepticism is reasonable. Similarities alone do not prove anything, but patterns matter, and the pattern emerging from the quantum realm is consistent, persistent, and deeply unsettling. Reality appears optimized. Reality appears constrained. Reality appears information-driven, and perhaps most disturbingly, reality appears to economize. The quantum world does not calculate everything at once. It waits, it responds, it updates only when forced to, which brings us to the most dangerous question of all. If the quantum realm behaves like a rendered environment, then what determines when reality is rendered? And more importantly, who or what is doing the observing? If reality truly behaves differently when observed, then observation is no longer a passive act. It becomes a force, perhaps the most fundamental force in the universe. In quantum mechanics, this problem is known as the measurement problem. A system exists in a superposition of possibilities until it is measured, at which point one outcome becomes real and all others vanish. But nowhere in the equations does it explain why measurement causes this collapse. This gap has haunted physics for nearly a century. Some interpretations attempt to avoid the issue by suggesting that all outcomes occur, branching into parallel universes. Others propose hidden variables we have not yet discovered. But none of these explanations remove the central mystery. Something happens at the moment of observation that changes reality itself. This is where consciousness enters the conversation. Cautiously, controversially, and uncomfortably. Early pioneers of quantum theory, including figures like Niels Bohr and John von Neumann, acknowledged that measurement could not be fully separated from the observer. Von Neumann even suggested that the chain of measurement ultimately ends in the conscious mind. Modern physics largely avoids this idea, not because it has been disproven, but because it is difficult to test. Consciousness does not fit easily into equations. It resists quantification. Yet the problem remains unresolved. In simulations, observation is not mystical, it is procedural. When a system queries a value, the program calculates it. Until then, the value remains undefined. This is not a philosophical choice, it is an optimization strategy. The quantum world mirrors this logic with eerie precision. Consider delayed choice experiments where the decision to observe or not observe a particle is made after it has already entered the system. Astonishingly, the particle's past behavior appears to change based on future measurements. Time, at the quantum level, does not behave as a fixed sequence. Cause and effect blur. The system seems to wait for the question before deciding what answer it has always had. This is not how a self-contained physical universe should operate, but it is how a system that calculates outcomes on demand would operate. Even more disturbing is the role of information. In quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or redistributed, but never erased. This principle, known as unitarity, suggests that reality preserves data at all costs. Why would the universe care so deeply about information? In computational systems, information preservation is critical. Losing data breaks causality, consistency, and reversibility. The laws of physics seem designed to protect the integrity of information above all else. Then there is decoherence, the process by which quantum systems lose their superposition through interaction with the environment. This is often presented as a solution to the measurement problem, but in reality, it only explains how quantum behavior becomes classical. It does not explain why one outcome becomes real. Decoherence describes the fade, not the choice. At this stage, the possibility emerges that observation is not about consciousness itself, but about interaction with a larger informational framework. Perhaps the universe does not care who observes. only that a query has been made. If so, then consciousness may not be the cause of collapse, but the interface through which collapse is triggered. And interfaces exist for one purpose: communication between layers. If the quantum realm is the lowest accessible layer, then observation may be the handshake between our perceived reality and whatever operates beneath it. If observation functions like a query in a system, then we must confront an uncomfortable implication. Reality may not be fully there unless it is being accessed. At large scales, this doesn't matter. Stars burn, galaxies collide, and time marches forward whether we watch or not, or so it seems. But at the foundational level, existence appears conditional. Quantum experiments suggest that outcomes are not merely revealed, but selected. The universe does not roll dice continuously. It waits until it must answer. This has led some theorists to propose that the universe operates under a principle similar to computational economy. Only the information required to maintain consistency at the observed level is resolved. Everything else remains in a compressed potential state. Compression is a hallmark of computation. In digital systems, vast amounts of data are stored in minimized forms until expanded when needed. Textures, physics, even entire environments exist as instructions rather than fully realized structures. The quantum wave function behaves in the same way. It encodes possibilities, not outcomes. Observation triggers decompression. This perspective reframes many of physics' strangest features. The uncertainty principle no longer feels like a limitation of measurement, but a boundary of resolution. The collapse of the wave function no longer feels mysterious, but procedural. And the apparent randomness of quantum events begins to look like entropy management. In a simulation, perfect predictability is dangerous. It allows the system to be reverse-engineered. Randomness, or something indistinguishable from it, prevents higher-level entities from uncovering the rules beneath their reality. This is not proof, but it is consistent. Even cosmic-scale phenomena reflect this pattern. The universe appears finely tuned for complexity, but not optimized for simplicity. Constants fall within narrow ranges that allow structure, but do not reveal why those values exist. From a simulation perspective, this is exactly what you would expect. Parameters are set not for elegance, but for stability. Then there is the strange silence of deeper reality. We can probe smaller scales with higher energies, but each step forward reveals not answers, but new limits, new walls, new minimums, and maximums, as if the system is designed to be explored, but not escaped. This does not mean we are characters in a game. It does not imply intention, purpose, or design in any human sense, but it does suggest that reality may operate according to rules that were not optimized for understanding. And that may be the most unsettling idea of all. If reality is a rendered environment, then its deepest layer may be inaccessible by design, not hidden, simply unreachable from within. Which leaves us with a final question for this section. If observation triggers reality to resolve, then what happens when observation ceases? Does the universe continue to exist in full detail, or does it return to potential, waiting to be asked again? If the universe is a simulation, then it should occasionally fail, not catastrophically, but subtly. Not in ways that break the illusion, but in ways that expose its limits. These failures would not look like errors. They would look like strange rules, and the universe is full of them. Consider the cosmic speed limit. Nothing can exceed the speed of light, not because of resistance, but because space and time themselves adjust to enforce that limit. As objects approach light speed, time slows, lengths contract, and mass effectively increases. Reality rewrites itself to prevent violation. This is not how a flexible analog universe should behave, but it is how a system enforcing a hard constraint behaves. Then there is the cosmic horizon. We can only observe a finite portion of the universe. Beyond a certain distance, space expands faster than light can travel, permanently cutting regions off from observation. No signal, no matter how old or powerful, can reach us from beyond that boundary. Reality, quite literally, has a render distance. At smaller scales, the same pattern emerges. We cannot probe beyond the Planck scale without destroying the very concepts we rely on to measure. Space dissolves into noise. Time loses direction. Our equations stop making sense. These are not just technical challenges. They are structural limits. Some physicists have suggested that anomalies in high-energy cosmic rays, unexpected alignments in the cosmic microwave background, or unexplained asymmetries in fundamental constants might be the closest thing to glitches we can observe. Not proof, but stress points. In digital environments, glitches often appear where systems are pushed beyond their intended operating ranges. Precision errors accumulate, approximations fail, boundaries reveal themselves. The universe behaves in a similar way under extreme conditions. Even black holes may represent computational shortcuts. Instead of resolving infinite density, the universe hides information behind an event horizon, preserving consistency at the cost of accessibility. Reality refuses to calculate what it cannot safely represent. This is not speculation alone. Black hole physics suggests that information is not lost. It is encoded at the boundary. Once again, information is preserved, structure is maintained, and deeper access is denied. A system protecting itself. At this point, the simulation hypothesis becomes less about who created the universe and more about how it behaves. The question shifts from who is running it to what kind of system is this? A training environment? A sandbox? A self-consistent informational structure without intent? Or simply a universe whose rules coincidentally resemble computation because computation is the most efficient way to structure reality? There is no definitive answer, and that uncertainty is important because belief is not the goal. Understanding is. The danger lies not in asking whether reality is simulated, but in assuming we could ever confirm it from inside. Any sufficiently advanced simulation would contain observers capable of asking this question, but not of answering it conclusively. The system would allow curiosity, but not verification. If reality truly is a computational structure, then one final implication becomes unavoidable. Meaning may not be embedded in the system itself. Simulations do not explain purpose. They explain behavior. They tell us how rules operate, not why they exist. And the universe, when viewed through this lens, behaves with perfect indifference to interpretation. The laws of physics do not guide us. They constrain us. This reframes humanity's place in the cosmos. We are no longer explorers of a boundless reality, but interpreters of a filtered one. Everything we observe is mediated, not necessarily by intention, but by limitation. Even if the universe is not literally simulated, the fact that it behaves like one is itself revealing. It suggests that reality may be fundamentally abstract, mathematical, and information-based. Matter becomes an output. Experience becomes a readout. And consciousness, our most intimate certainty, may be the most foreign element of all. We experience time as flowing, yet physics treats time as a dimension. We experience choice, yet equations evolve deterministically. We experience meaning, yet the universe remains silent. If this is a simulation, then consciousness may not be native to it. It may be emergent or imported, a user process running inside a system that did not evolve to host it. That idea is deeply unsettling. But there is another possibility. Perhaps the universe is not a simulation created by something else. Perhaps reality itself is the simulation, a self-organizing informational structure that generates observers capable of questioning it. In that case, there is no outside, no creator watching from beyond the code. There is only the system, running itself, asking itself questions through us. The glitches, then, are not errors. They are reflections. They appear when the system encounters its own limits, when it cannot fully explain itself without contradiction. And maybe that is the point. A reality that could be fully understood would be static, finished, closed, but a reality that resists understanding remains alive, dynamic, open, and endlessly interrogated. The quantum echoes we detect are not messages telling us what reality is. They are reminders of what reality cannot be, and that may be the deepest truth we are allowed to glimpse. When I first started exploring these ideas, I wasn't trying to prove that reality is a simulation. I was trying to understand why the universe feels so precise, yet so incomplete. The more I looked into the quantum world, the more it felt like reality doesn't reveal itself freely. It responds only when questioned. That doesn't make existence meaningless, but it does make it fragile. If we are inside a system, then our curiosity isn't a bug, it's a feature. And maybe the real mystery isn't whether this is a simulation, but why a universe that may not care about meaning still gave rise to minds that desperately search for it. That question, more than any equation, is what keeps me looking into the dark. This is where the light ends. Thank you for watching. And remember, some questions are meant to remain unanswered.